Broadcast is now starting. All attendees are in listen-only mode.
Good morning and welcome to the February Pacific Northwest DEWS Drought and Climate Outlook webinar. Happy New Year, since this is the first time we're seeing everybody or having everyone join us since the beginning of 2022. My name is Britt Parker and I'm with the National Integrated Drought Information System. This bi-monthly webinar series hosted by NIDUS and the USDA Northwest Climate Hub and Oregon Climate Change Research Institute is designed to provide partners and other interested parties in the Pacific Northwest with timely drought and climate information. Each webinar will be tailored to reflect recent and current and forecasted conditions and climatic events, but will also include discussions of observed impacts and other relevant updates from across the region. Webinars and recordings and other supporting materials will be posted on drought.gov later this week, and you will receive an email with the recording link. After today's webinar, you'll have the opportunity to provide feedback that will help us improve this webinar series, so please take a moment to tell us what you think. Before I go into today's speakers, I want to thank everyone who answered our post-webinar questions last year towards the end of the year. We do appreciate your feedback and we do use it to improve upon the webinar series. One question we added for the last couple webinars in 2021 was concerning the number of speakers and if there was a preference for 3 or 4 speakers. The response was mixed, though the majority wanted to continue with 4 speakers. We've also seen feedback over the years of wanting to hear more about how the science, tools, and products that are presented could or are being applied, and the desire to hear more from practitioners who are taking action to build resilience to drought and to adapt. To that end, we're going to try an approach where the final 2 presentations are paired such that the first is on the latest science or a new tool, with then a presentation from someone who's applying that information in the real world. So if you have ideas for presenters or feedback on this new approach, please reach out to me and fill out our post-webinar survey after today's webinar. So without further ado, our speakers today include our climate recap and current conditions from Nick Bond with the Office of the Washington State Climatologist, seasonal conditions and climate outlook from Andy Bryant with the National Weather Service Weather Forecast Office in Portland. We'll then have a series of 2 talks on Beaver Pond Influences on Downstream Temperatures on the Umpqua River Basin, Oregon, with John Stevenson at the University of Oregon. And then our final talk will be Damned If You Do, Damned If You Don't, Lessons Learned from Designing, Permitting, and Monitoring Beaver-Related Restoration Projects in the Western U.S. Before we begin the presentations, we wanted to highlight the partners who make this webinar series possible. The Northwest Climate Hub develops and delivers science-based, region-specific technologies and practical information that will assist agricultural and natural resource managers with climate-informed decision-making in Idaho, Washington, Oregon, and Alaska. Visit their website to learn more information. We also are sponsored by or hosted by the Oregon Climate Change Research Institute, which is a network of dozens of researchers at Oregon's public universities that work closely with other public and private entities. OCRI is housed at Oregon State University and advances understanding of regional climate impacts and adaptation and cultivates climate-informed communities. NIDUS was established in 2006 by public law with a mission to improve the nation's capacity to proactively manage drought-related risks by providing those affected with the best available information and resources to assess the potential for drought and to better prepare for, mitigate, and respond to the effects of drought. NIDUS is building the foundation of a national drought early warning system through the development of regional DEWS, or drought early warning systems, where networks of partners and stakeholders share information and actions that help communities cope with drought. While the ultimate goal is a national early warning system, we recognize the impacts in early warning information differ across regions, and each DEWS has many of the same base ingredient, but ultimately have their own flavor to reflect the needs of their regions. The Pacific Northwest DEWS was officially launched in 2016, and our strategic action plan and information on current activities is available on drought.gov. To facilitate our early warning system, more precipitation and observations are needed. We encourage you to join COCORAS, the Community collaborative rain, hail, and snow network. This unique network is a nonprofit, community-based volunteers of all ages and backgrounds working together to measure and map precipitation, as well as condition reporting. Observations by COCORAS observers of precipitation events or the lack thereof are important to capture and improve our understanding of weather. To become a volunteer or to learn more about COCORAS, visit cocoras.org or contact your state coordinator. And at the end of the presentation, I will put all of the coordinators' information in the chat box, as well as the links for the next couple slides where I highlight things that are happening around our drought early warning system. So I just wanted to flag that the 2021 Pacific Northwest Annual Water Year Impact Assessment is now available. The purpose of this assessment is to summarize the water year conditions and sector impacts as a resource for future management of drought and other climate extremes. Thank you to the author team and all that contributed to the annual water year meetings and impact survey that went into the report. And like I said, I'll throw that link in the chat box in a moment. We also wanted to highlight a series of workshops from EPA's Creating Resilient Water User Initiatives on building resilience and adapting to climate change impacts for drinking water and wastewater utilities. These virtual workshops will focus on conducting a climate change risk assessment using EPA's CREATE tool. And the audience is drinking water, wastewater, and stormwater utility owners and operators, as well as other water sector stakeholders in both Alaska and the Northwest. And we'll post those links momentarily. Finally, I just wanted to flag that the U.S. Geological Survey and NIDIS are hosting a series of listening sessions on drought prediction to seek input on priorities and needs related to predicting water availability changes under drought conditions at national and regional scales. This input will be used to guide USGS drought program planning and orientation, as well as to inform other national drought programs. They've already held the introduction to the listening session, and you can find a recording of that on drought.gov, but there are a series of 4 more listening sessions throughout 2022. And so with that, I'm going to hand over the control to Nick Bond, who's going to give us an overview of the current conditions and climate recap. And Nick, hold on one second. I'm finding you in the list. Here we go. Great.
Oh, so I will be, okay, gotcha. I'll be showing my screen here. Hang tough. And, where am I? Okay. So what you should be seeing is, let me.
There we go. Great.
Okay, let me get this panel out of the way. You should be seeing a time series of Northwest average temperatures for the months of December and January in the upper left and precip plot in the lower right. You look at this and go, well, the last year looks pretty normal for this middle of winter. Maybe there's not much to say, and I should just turn it over to Andy for the update. Well, there actually is something to say. And in particular, with apologies to Dickens, it's kind of been a tale of 2 winters. While it wasn't that long ago, we had some really wet weather here in the Pacific Northwest. This is a scene the first week of January over a small airport in southwest part of Washington State. And what's kind of nice here is whether you're a wheeled aircraft or a float plane, you could use the same airport was available, right? And we had a lot of snow in the mountains, and in fact, a unprecedented sort of length of road closures across the Cascades of Washington State, at least. It actually led to some supply chain issues. Note the highlight at the bottom, grocery stores there was no chicken at all. So, you know, we're talking hardship. Going back to early January, oh, misspelled January there. The snowpack across the Northwest was in pretty good shape. This shows the SWE relative to normal for that time of year, with individual stations and the basins colored in. Greens are good, blues are great, and whites are okay. And, you know, we were in good shape. But then by last week, real deterioration in conditions. And yeah, just in terms of SWE, this is for the 23rd of February. We can see that most of the Northwest is below normal snowpack, with the exception of the Coast Range of the Northwest Oregon. And so things have really changed. And again, just points out that kind of the whipsaw that this winter has been. If we look for the water year as a whole, up through last week, in the upper left is temperatures relative to normal, and to the right, precipitation as a percent of normal. And much of the Northwest has been on the warm side. The interior low elevation spots, in particular Snake River Valley and parts of the Columbia Basin of eastern Washington, have been a little cool. It's been mostly drier than normal everywhere except for the basically western Washington. All right. But then, you know, the middle of January into February hit us. And while the temperatures have been on the warm side in the mountains, what really is notable is how the faucet shut off. And here for the 30 days ending last week sometime, you see that on the right, the precipitation map of the percentages relative to normal and down, you know, in the 20% range or something. Here's an example of an accumulation precipitation from Burns, Oregon, in the lower graph, showing that almost no precip from the first week of January through much of February. We're getting some right now. And again, I'd like to tee up Andy for what he's going to be telling us about what we can expect for the remainder of winter. But yeah, quite a notable dry section. What was going on? Well, most of the time, it's a La Nina winter. Most of the time when we have La Ninas, there's a weaker than normal Aleutian low. There's higher geopotential heights than normal over the central North Pacific. The consequence, this shows an anomaly map, 500 millibars of stronger than usual northwest flow into the Pacific Northwest, and especially on the western side of the Cascades in the northern part of the Pacific Northwest. This gives cool and wet conditions. Well, what actually happened again during this really dry spell was that that pattern was in some ways similar to what we've seen during previous La Nina winters, but it was all shifted to the east. And so higher heights than normal extended well into Western North America, and just not a very wet pattern at all. And with these high heights, kind of stagnant weather conditions, that's also contributed to the low elevation, kind of cool temperatures in the interior Northwest. I'm going to go out on a limb here and speculate that that may be, just maybe, associated with what's been going on in the tropical Pacific. Direct your attention to the lower panel here that shows sea surface temperature anomalies for a week there in early February during the height of our temporary, at least temporary drought, and how this cooler than normal sea surface temperatures in the tropical Pacific are mostly in the eastern part, and in particular, they're some warmer than normal water around New Guinea and the Indonesian maritime continent, but not as warm as it was last year, not as warm as it usually is. And so conceivably this eastward shift in the whole La Nina pattern is at least in part associated with the eastward shift in the circulation anomalies that brought us our dry weather. A little bit more about how dry it was. It's especially the case in eastern Oregon, as illustrated in the total moisture percentile map here shown at the left that takes into account both soil moisture and the snowpack. There are some places in the Cascades that are doing okay. The stream flow map shown at the right shows kind of a similar story here. The brown and red dots show where stream flows are much below normal for the time of year. The greens are in that broad range near normal. There are a few blues showing above normal. I'm not as worried about the west side of the Cascades as kind of the interior Northwest. And you can see, especially in the Snake River and its plain, that pretty low stream flows there. And so that is a real concern. Thanks to the help of Larry O'Neill, the state climatologist for Oregon, a little bit more about water. He has this nice depiction of reservoir storage across that state. And again, typically reservoirs on the west side of the state are left less than capacity for flood control purposes. What's alarming is some of the big reservoirs on the east side that are hundreds of thousands of acre feet below their usual storage at this time of year. And so that's, yeah, obviously very concerning. Yet another look at that sort of thing is from the Bureau of Reclamation sets of reservoirs and the teacup diagrams they used to summarize that. I want to show on the lower right here for the Upper Snake River Basin, how those teacups, especially in the big reservoirs, are a lot less full than we like, and with the low stream flows, that's going to be problematic. It's especially bad in southwest Oregon right now, and you can see those reservoirs are just don't have very little water in them, and some of the stream flows on these admittedly small streams, but we're talking, cubic feet per second in the single digits. The Yakima Basin, on the other hand, in the upper left, is in better shape, and so Washington is doing better there. All that is summarized in the recent U.S. Drought Monitor depiction shown here, with plenty of this red and brick red colors that we really hate, and especially eastern Oregon is in a lot of its areas in D3 and D4, and I wouldn't be surprised if Idaho is going to be getting redder with time. The idea of putting the onus on Andy that we could get enough rainfall and mountain snow to get out of this winter seems very unlikely, especially east of the Cascades. The amount of precip we need in the next 2 months just to ameliorate, not eliminate, but ameliorate the drought is above 200% in these brownish regions here. And the percentage of that in some places less than percent, maybe 5 or 10%. So Andy's got a tall order. So again, we had a real dry period in the middle of this winter. Quite a surprise, stuff happens. And that's reflected in the drought depiction from us, especially the interior Pacific Northwest. I'm suggesting that maybe we can blame just how the SST anomalies played out in the tropical Pacific in part. And again, I'm very anxious to hear what Andy is going to say. And with that, I am done. And I will stop showing my screen.
Great, thanks, Nick. I'm giving Andy control of presentation mode.
Okay, this is Andy. I'm checking if you can hear me first.
I can, yep.
Okay, that's a positive start. And let's see. I believe I'm showing my screen, but I need to verify if I'm showing the right one.
We're seeing your
email. You're seeing my email. Shoot. Okay. So let me.
There we go.
Normally I would be actually working from home, but I'm in the office today because we're dealing with some flood potential in our area today. But I'm using a multiple monitor setup that I don't typically use for these presentations. So let me start the show. Okay, so I'm checking again. Are you seeing my main screen for my presentation?
Yes, it looks great.
All right, so I'll go ahead. I will be talking about the monthly and seasonal outlooks today. I am feeling a lot of pressure from Nick to deliver something that people want, but I'll just try and stick to what we think is most likely to happen. I'll be touching on how we expect ENSO conditions to evolve, and then looking at water supply. I was going to show almost identical reservoir graphics as to what Nick just showed, so I've eliminated that from my presentation for now. And then finally, what we expect to happen with evolving drought conditions. So I want to touch on the short term to start with, and I need to explain these graphics a little bit. On the upper part of the screen, you see graphics from the Northwest River Forecast Center. And this shows the sum of the next 10 days of precipitation, including today. And on the left is the total of what's in the forecast for the next 10 days. And then on the right, it shows that in terms of the percent of climatology for that same period. And the big thing to emphasize with this is that, yes, for much of the Pacific Northwest, it's going to be pretty wet over the next 10 days. But for many of the areas that are currently in extreme drought or worse, we're going to see below average precipitation even in the midst of a fairly wet pattern over the next couple of weeks. The lower part of the screen are graphics showing the 8 to 14 day outlook from the Climate Prediction Center, emphasizing the likelihood of below average temperatures, but also leaning towards below average precipitation. So what it's looking like is once we get through the next 5 days or so, where we'll have some fairly heavy precipitation, it goes back to a fairly quiet pattern. Now, that said, the outlook going to the next screen for the month of March, this still is, and this is from mid-February, so you know, it's up to you to decide how much weight you want to give this, but the overall monthly outlook, and a lot of this is influenced by what's happening with La Niña conditions, is for the likelihood of below average temperatures and above average precipitation, which if that played out, that would certainly be beneficial throughout the Pacific Northwest, given the dry conditions that we've had over the past month that Nick highlighted. So I want to pause for a moment here and just show some monthly precipitation normals for a few locations around the Pacific Northwest. I know this is kind of a busy table, but what I'm showing here is for Seattle, Portland, Medford, Spokane, Pendleton, and Boise. I'm showing the monthly precipitation normals and then the percent of the annual normal that that monthly total represents. And the thing that I'm wanting to represent, to point out here is that we're most of the way through the wettest part of the year. And March is really our last, what we would consider a wet month climatologically for much of the Pacific Northwest. There are some exceptions when you get into eastern Oregon and southern Idaho, where we can have some significant totals relative to the annual precipitation normal in all the way through May and June. So when you look at October through February, for areas west of the Cascades, that represents about 2/3 of your annual precipitation totals. East of the Cascades, it's somewhere between 50 and 60%. So again, we're most of the way through the wet season for much of the Pacific Northwest, and our monthly totals drop off rapidly. The reason I've highlighted March through June is that that's the time period that I'll be emphasizing in the next graphic with the seasonal outlook. So again, I've already touched on March, the idea that CPC is leaning towards above average precipitation and below average temperatures. So before I get to the seasonal outlooks, let me just talk about where we are with La Niña conditions. And the predictions for this have been pretty consistent through the winter, that as we get towards summer, that we're going to transition back to ENSO neutral. And so the graphic on the left it shows various models that are used for seasonal predictions of ENSO conditions, El Nino Southern Oscillation conditions. And where we are right now is in weak La Niña conditions. And the consensus of the guidance is that by late spring or early summer, we will transition back to neutral conditions. Actually, really the consensus is that that's going to happen sometime during the spring. So the graphics on the right are a couple of different depictions from the Climate Prediction Center about how ENSO will evolve and what's most likely in terms of La Niña neutral conditions or El Nino. And so again, it just highlights that the expectation is that by late spring, we'll be back to neutral conditions. I'm going to show the seasonal outlooks now for the April, May, June period, and then I'm also going to show the outlook for the June, July, August period. You can look at any 3-month combination from the Climate Prediction Center. So I kind of arbitrarily selected these two. Looking at April, May, June, the thing that we're mainly looking at is what's the likelihood for above or below average precipitation? Because that we are still in a period where above average precipitation would significantly help drought conditions, but that is not what's most likely according to this outlook for the April through June period, especially for the areas that are most significantly affected by already multi-year drought. And then Nick highlighted how there's evolving concerns about drought conditions in southern Idaho. And so that's all, most of Oregon and most of Idaho are in that area of enhanced probability of below average precipitation. Temperatures leaning towards below average, especially for western and northern Washington. Then moving ahead to June, July, August, and I selected these months because, you know, really by the time we get to June, we typically are mostly dry and starting to have the possibility of warm temperatures. For many of us, we're scarred by the memory of what happened last June, which was really so far out of the realm of what we would expect as a possibility for June temperatures. But looking ahead to this June, July, August period, throughout the Western U.S. and really most of the continental U.S., we're expecting above average temperatures. That signal is certainly stronger for the Southwest than what we are expecting for the Pacific Northwest, but really what we would hope for is something near or below average for temperatures to slow down snowmelt in the late spring and early summer. And then the outlook for precipitation for June, July, August is for an enhanced probability of below average precipitation. The totals, again, as I showed on that table a little bit ago, are typically fairly negligible, but any precipitation will be welcome as we go through the spring and summer for the Pacific Northwest. I wanted to touch on water supply volumes, what's being forecast, and this is another way of basically taking, you know, kind of accounting for everything that's happened with snowpack, seasonal precipitation, soil moisture conditions, and reservoir control, and encapsulating this in watershed volume forecast. So when we talk about a forecast volume, we're talking about the total amount of water for that April through September period, and how does what is forecast for this year compare to the long-term average for that watershed. And so a lot of these numbers match up, you know, kind of just, you can see that looking at the colors here, as to where we've seen dry conditions through this winter and where we have ongoing drought concerns, really multi-year drought concerns for much of central and southern Oregon and other parts of the Pacific Northwest. You know, southern Idaho, as Nick talked about, is an increasing concern. So the green represents near average, yellow and orange increasingly below average, and then red is much below average. And so we see that across much of central and southern Oregon. On the lower left is a graphic just grabbing a snippet of the forecast area for the California-Nevada River Forecast Center. That River Forecast Center does the water supply forecasting for the Klamath Basin. So that's what's being shown there. That's one of the areas of Oregon that had multi-year severe drought impacts. And it's looking like much below average, on the order of about 50% of average for the April through September water supply volumes there. Taking a look at the seasonal drought outlook from the Climate Prediction Center, most of Oregon is highlighted as drought persisting, and I think we may see some expansion of areas going into extreme drought or worse. And then for parts of Washington, we see drought improvement or even removal likely over the next couple of months. And then, as we've talked about for Idaho, increasing concerns about drought persisting or even expanding there. To summarize what I've talked about, we're expecting near average precipitation and water supply for much of Washington and northern Idaho, below average precipitation and water supply for Oregon and southern Idaho. And again, that's for the spring through summer period. Spring temperatures likely to be near or below average, especially for much of Washington. Summer temperatures are likely to be above average across the Pacific Northwest. And there are compounding drought concerns for areas already dealing with multi-year drought in much of Oregon and southern Idaho. And that is all I have, and I will pass it back to you.
Great. Thank you, Andy. And I'm going to pass presenter mode on to you, John, for our next presentation, and just flag that Holly had just put in the chat box. We'll be trying to put the questions and answers in the chat box just because we're running a little bit behind today. So take it away, John.
Great. And Brett, can you see and hear me?
Yes, all good.
Great. Awesome. Well, thanks everybody for and the invitation. I just want to share some of the work that we've been doing in southwestern Oregon in the Umpqua River Basin, considering temperature effects from beaver dams. And since I am the second of, my literally computer just froze, there we go. But since I'm the second of two speakers on the topic, I just wanted to provide a very brief kind of introduction to this notion of beaver-related restoration for those of you who aren't familiar with it. These are two documents I highly suggest you take a look at if you're interested in this topic. But what we're really talking about, and particularly as we think about drought, is how do we improve some of the the ecosystem, the physical and ecosystem functions that particularly in impaired watersheds could have, or at least the potential. And so it's gone by many different names. Stage 0 is a common term for the type of restoration that we're talking about. And you can take an impaired watershed and, so in this case, this top left diagram, that is fairly incised, narrow, and in particular, fairly disconnected from its at least the floodplain is fairly disconnected from the groundwater. And so what we're trying to do ultimately is use beavers to essentially facilitate or accelerate what is otherwise can be a natural process of channel widening and increasing complexity, which you tend to see depicted here as you move from left to right and down. And then ultimately into this bottom right-hand panel where you see a very complex stream system that's multi-threaded, and then again from the drought and storage component, ground and surface water interactions that are much stronger than that top left panel. So these are the types of things that are at least hypothesized and hoped for when we start thinking of beaver-related restoration. There's been some work looking at how frequently is this being used across the West, and what they found is that increases in late season flow in particular have been some of the most commonly cited objectives of this type of watershed treatment, and ultimately really trying to reconnect surface and floodplain or surface and groundwater connections by capturing sediment and kind of rebuilding these stream beds. And then the hope that these high flow periods during the winter will be pushing off into adjacent floodplains and then essentially stored as shallow groundwater that are released later on in the season when we most need it. From a quality perspective, the sediment retention I already discussed, and then there's some, there's been a mix of work on temperature, which is really where we focus our efforts, suggesting that possibly beaver dams can warm temperatures in the winter and then possibly cool temperatures in the summer. But it turns out that when you look at a lot of meta-analyses across all of the studies that have done upstream versus downstream comparison, at least with temperature, we find that increases in temperature are just as common, if not more common, than downstream cooling. So in our basin, the Umpqua, that presents a pretty big challenge because on the one hand, watershed managers know that that anadromous fish species, and in particular coho salmon, which are a huge management concern for the basin, use beaver ponds in the winter, particularly as juveniles, to kind of get away from these high velocity flows during winter. But temperature is a huge limitation as well for this species in particular. You know, and I was just, the state of Oregon has classified, I think it's over 85% of the locations where they have sufficient data monitoring temperature with reference to the regulatory limits. 85% of those locations exceed maximum temperature thresholds in the summertime. So temperature is also a really big deal. So our study really tried to focus on three things: understanding what is the dominant downstream effect of existing beaver ponds or pond complexes in the basin, and then secondarily, you know, how far do those do any changes persist downstream, either as a cooling or as a heating effect? In other words, do they have large longitudinal impacts, or are they very localized? And then lastly, we also looked at dissolved oxygen, which I won't talk about, but I do have a few slides at the end if people are interested from questions. So I'll just step back and think, you know, pond or, you know, stream heat budgets are really complex. And when you impound water, two important things tend to happen. Is that one, you're slowing water down, so it's going to, and then you're spreading it out. And so what you're ultimately doing is, at least at the pond surface level, is you're increasing its exposure to solar radiation, which tends to have a warming effect. Conversely, you know, cold water also tends to be more dense and tends to, you know, kind of fall or collect at the bottom of these pond systems. And we also know just from basic physics that, you know, as you stack water up, the weight of water of a water column on the pond bed is significant and can actually push water into the channel bed or pond bottom bed at this point, and actually create these shallow subsurface flows that can travel beneath the beaver dam. So when we think about what the downstream effect is, you know, one of the first questions we have is, where's this water coming from? Is it spilling, you know, hot water that's been heating in the surface in the sun, either over the top of the dam or around the sides of the dam, in which case you might expect a heating response downstream, or do these shallow hyperrheic flows, you know, consist or make up the dominant downstream discharge? And so we presented a study design, or used a study design, where we tried to capture upstream versus downstream distances. And so we did that through, you know, 5 temperature monitoring locations upstream, 5 temperature monitoring locations downstream, that we compared to the average of those upstream conditions. So I'll talk a little bit about those anomalies downstream, or in a few slides. And then additionally, we monitored pond surface and pond bottom temperatures. And then we did this across 7 study sites. And I should just note that we monitored this on an hourly basis across June, July, August, and September of 2019. And so what we've done is plotted essentially the downstream temperature, the average downstream temperature across each of those locations by month, minus the average upstream temperature. And so in June here, what you can see is that this 0 meters, so this is the temperature monitoring location immediately below the dam, was, you know, on the order of nearly 2 degrees C, you know, 3.5, 4 degrees Fahrenheit warmer than its upstream location. So pretty notable warming signal immediately below the dam. And then at, you know, 100, 200, 300, 400 meters downstream, you can also see that the average noted by these shapes, you know, anomaly or warming signal, you know, was greater than the reference, but it tends to attenuate or decrease as you move away from that dam. And this makes sense. So you basically get a big heat pulse coming, or a heat pulse coming out of the dam that tends to decrease as you move away from the dam. And then it turns out that if we look at this on the seasonal, across the season, is that same pattern of longitudinal warming persists across all months, but it tends to be most accentuated in June and July, and then tends to be more minimal in August and September. So then I also mentioned that this question of, well, where is this heating coming from, and can we predict that based on, where's the water coming from, and can we predict the downstream response based on the source of that water? Well, so what we did is we ran a number of logistic regression models to basically use the pond surface or pond bottom temperatures to predict downstream temperatures. And so what I've done is I plotted the R squared on these right-hand panels, which basically is a series of numbers. And so in this case, you know, the pond bottom noted by the orange 72 suggests that 72% of downstream variation is explained by the pond bottom temperature variations, at least in June. You can see that number increases to 80% in July and is about 80% in September, but it's very, very low in August. Conversely, pond surface temperatures, you know, really ranged between less than 50% down to 14% throughout that study period. So the big take home here is that it would appear that there's a much stronger coupling between the temperatures at the bottom of the pond and the downstream extent. What's interesting is that conventional wisdom is typically, at least in the northern hemisphere, that summer temperatures influenced by shallow groundwater systems tend to decrease, right? Because groundwater systems tend to be a little bit colder than the surface temperatures in the summer. That's not what we found. And so to kind of explain this, we went ahead, and I don't have any figures on this, but we compared the pond bottom temperatures to our reference temperatures, so those upstream averages. And what we found is that pond bottom temperatures turned out to be warmer in June and July, but colder in August. And so this more or less suggests that even though we're vecting or transporting water through the subsurface beneath these dams, or at least that's the presumption, that the water is already heated, and so it kind of tends to undermine those expected cooling patterns. So just to wrap up here, what we found is that warming was common below beaver dams, especially in June and July, but that signal was fairly localized near the dam, and that warming water appears to be the result of warm water transported below the dam. And just some concluding thoughts, our findings are consistent with other studies that have shown downstream warming. And then at least for us in our basin, success really depends on the specific goals of your project and some of the site level processes. And that at least in the Umpqua, you can't always assume that beaver-related restoration is necessarily a no regret strategy. And I'll just acknowledge some of our funders from USDA National Wildlife Research Center, USGS, and then the North Umpqua Foundation in particular that's helped a lot with my field work. And I think we're going to just jump on to Caroline there.
Great, thank you, John. And yes, we'll go straight to Carolyn, and I am giving you control over the presentation now. Perfect.
Great, thank you. And let me move this because similar to Andy, I've got a multiple screen situation here. And that GoToWebinar is not playing nicely with. Sorry, what do you see? I'm very confused.
Yeah, so we saw the edge of the presentation, but we're seeing your other screen. It's just
okay. Sorry, I'm really trying to. No. All of the controls are right where I'm trying to move my presentation from. Here we go. Okay.
There you go.
So just as John teed up, I'm talking about. So my name's Caroline Nash. I'm the principal technical consultant at a project incubation firm called CK Blue Shift. And what we largely do is work with project managers, NGOs, municipalities, and a variety of other land managers and owners around the West to try implementing watershed scale restoration conservation projects, largely aimed at drought and climate resilience. And I'm realizing, are you seeing the presenter view again now?
We are, I'm sorry.
Oh my goodness, I'm sorry. This is a real, I thought I had it all planned out. Okay, let's try this again. Okay, it just is not working. So I'm going to try something else.
Okay.
Which is you're just going to look at PowerPoint. I'm sorry about that, but GoToWebinar is not letting me change which screen gets shown. So as John mentioned, when we're in the world of implementing beaver-related restoration, I think it's really important to acknowledge that there are a range of words that are used to describe functionally a similar process. So, a dam by any other name still is ultimately aiming to impound water. And so variously throughout the West, you'll see things called plugs, beaver dam analogs, artificial beaver dams, check dams, weirs, aggradation structures. This is a photo from the Northern Sierra where they use a pond and plug tactic. And ultimately what I just want to emphasize is that the goals through a lot of these in terms of the mechanism by which they're hoping to create change is to increase roughness. So increase the resistance with which water encounters as it moves through a valley floor so that it slows down, spends a longer amount of time in that valley floor, and in so doing increases its position, the elevation of surface water relative to the channel banks. This accounts for some of the warming processes that John was just talking about, but those warming processes are sort of coupled in this case with a hope that by raising the water levels in the channel itself, you'll change the surface water groundwater interaction to the floodplains and aside. And as John mentioned, this can work differently depending on those site level processes. So what we see in places that are often high in a watershed or a gaining reach, where streams tend to increase, groundwater is discharging to the stream and increasing stream flow as we move downstream. The way that the mechanism by which this works is that the increase in surface water level within the channel reduces the gradient of groundwater flowing to the channel, helping it sort of plug back up. It's like putting a blockage, slowing down the faucet on a tank of water so that more water gets held up there. In a losing region, typically found further down in a valley system or in an alluvial floodplain, you tend to see situations where the surface water in the channel is the source of water to the floodplain. So that's a reverse surface water groundwater gradient and pushes water out. And just to give you a sense of what these look like, so these are some typicals that are often used in the grant or the permit applications that we use to acquire the necessary permits to do this work from the Army Corps of Engineers, the EPA, state historical preservation offices, state water quality offices, and if we're working in around federal ground or with federal money, of course, there's the entire NEPA processes. And so this first one is called variously a postless BDA, a log jam. When we're working in the sort of dry Intermountain, Eastern Oregon, Washington locations through to Montana, Colorado, it bears a lot of similarity to the large woody debris jam structures you might see in the Coast Range, but we're just working with smaller material. And in many ways, this isn't so much mimicking beaver dams as it is mimicking the process by which senescent riparian vegetation, which you can sort of see in this photo of the site down below, as it dies, it falls and collects in the channel itself, because these small streams in particular rarely have enough stream power to mobilize large wood. And so you get these massive accumulations of woody material. And the sort of degradation that drove the removal of this was that there were a lot of federal policies, state policies around removing riparian vegetation through the 20th century as a way to facilitate more water availability. And so I think a key thing to emphasize from a practitioner standpoint is that, folks are almost always trying to do the right thing, and as our information evolves, so too does our approach. And so, best intentions, there's always going to be something we're doing now that we look back on and think like, well, shoot, maybe that wasn't the best idea. And so this is one of those instances where some of these structures can really serve more so, not so much to restore beaver and the role of, beavers in a landscape, but actually restore the role of having riparian vegetation in a landscape. Another one that you see really commonly and that John mentioned are these beaver dam analogs, or brush dams in other cases. And so these are pretty common throughout Oregon in particular, where you see a sharpened fence post that's installed sort of pretty deeply into a channel as a way, and materials woven between it. Oftentimes you see an accumulation of material behind the structure to help plug it up, but from the surface it looks like it's pretty much just made of wood. These are called beaver dam mimicry structures, or beaver dam analogs, but actually they bear most similarity to, in this case in the lower, you see a photo of Zuni brush dams. And so these are techniques and technologies that were really developed and deployed by indigenous land managers over millennia. And so there is actually a lot more similarity of these BDAs to structures that humans have built. But again, like a beaver dam, like anything, ultimately they're trying to impede the downstream flow of water either by slowing it, halting it, and spreading it out. Finally, we have aggradation structures, artificial beaver dams, earthen structures, you name it, alphabet soup. And these are earthen structures that are intended, again, same function, but are often deployed in landscapes where there's very limited riparian vegetation, such that you really want to keep whatever vegetation you still have available. So it's a lot of the decisions around how these structures get built and how they get deployed is contingent on what's available in the surrounding landscape. And what I really wanted to focus on with this is to give you an example of what some of these demonstration projects look like and some of the constraints we're under as we're designing them. So this is a demonstration project that's been worked on in Montana on all private ground. And I really want to emphasize how important it is to have private landowners as partners in this, because as I mentioned briefly previously, one of the biggest constraints to project siting, location, prioritization, monitoring, everything is the permitting and regulatory processes. And of course, these are necessary, sideboards to make sure that we're not implementing more harm or doing making sure we're keeping things above boards, but the timelines associated with some of those processes, the costs and some of the pre-development work can really limit where you're able to function. And in the case of public land, that NEPA process and a lot of the workforce limitations that currently exist around it can mean that the timeline to get a NEPA approval to do, so this is your National Environmental Protection Assessment timelines, anytime you're on federal land or using federal funding. I have project sites where one of the federal partners is unable to run a NEPA in a 5-year time period, and our grant funding runs out in 3. So, we really have to prioritize places where we can deploy that funding within the time frame allocated to us by that funding. And that's where the private landowners come in. This is entirely privately held. And to John's point, this is in fact one of the ways that we've really tried citing locations that are truly experimental. There is not a lot of science documenting what happens at scale. This is a warm water fishery environment, so that we didn't have as many concerns about the deleterious impacts of having warming temperatures downstream on critical trout habitat, for instance. And this was an entirely dry stream that we were working in. And so we did, while there's no such thing as a no regrets creek, there is an emphasis of trying to find locations where the worst possible consequences won't ultimately damage wildlife, human values, or anything beyond repair. And you can see it's a pretty large area. This is about 6 miles of stream with a high density, little bright green marks of structure locations. And the implementation of the structures is largely meant as a way to create redundancies, both for structural pieces as well as to increase the amount of water surficially and subsurficially, to create the kinds of riparian responses, to create the kinds of changes in surface and groundwater. One of the big limitations we have for the goal is with a lot of these is monitoring, but I'm sure many of you are familiar with when you have federal funding, often there will be a stipulation of it'd be great to have monitoring, there's very limited funding for it, so you kind of have to work with what you have. In the case of projects targeting groundwater, this can get really challenging because digging a groundwater well, especially in a very rural part of the county, can be extremely expensive. And so again, one of the values of working with these private landowners is we've partnered, you can see some of the folks we work with here, where they'll reallocate the use of some of the wells that they use for their pipeline systems, for their spring development, for their cattle ranching. And there we were, some of the cowboys were learning how to deploy hobo pressure transducers to start putting out into the wells and checking them there. And similarly, when we're putting in, you can see a beaver dam analog or a brush dam over to the side. One of the other big issues that we face is that the federal assumption of costs, a lot of these projects are built on an assumption of volunteer labor, but when we had our project partners spec out what it actually does in fact cost for them to have staff do this work, it was nearly triple what the federally listed cost of installing it. A beaver dam analog is expected to cost $27 to build per the NRCS CPS guidelines, so that's their conservation practice standards. That lists how much federal funding you can get for something. And these landowners said it was minimum 90 up to 110 just in terms of time, diesel, driving out there. And so really acknowledging the true value of human labor that it takes to do this is critical to getting both the funding done as well as acknowledging and sort of accessing monitoring networks to be able to get any kind of information. I'll skip through quickly here to the end, just since we are tight on time. There are a lot of opportunities that we're seeing with here, again, compared to a lot of traditional restoration techniques. It's pretty cheap, potentially scalable, and there are quite a bit of federal and state funding opportunities if you can get them, and some emerging finance strategies. You can see here a photo from Klamath Falls, Oregon. This was taken by Charlie Erdman at Trout Unlimited. Looking at a natural beaver dam complex amidst the bootleg fire. And so you can see the real value of these, it doesn't take much monitoring data to look at this and see some of the value of what is potentially going on here in the midst of a fire-scarred landscape. But as John mentioned, there's still a lot of challenges, both related to research of understanding the scaling. As we instrument these projects in the case of temperature, we still don't know what happens if we implement 3 structures. Maybe the amount of warming is small enough as to not be, put our stream out of compliance with water temperature regulations. But if there is a linear scaling of temperature increases as we scale up, what kinds of trade-offs are we getting between water availability and water temperature? Similarly, there's a lot of funding and regulatory constraints that still really limit our ability to target the locations of these projects to some of the places where they might be best best treated. And again, here's where I'll emphasize the real value of partnering with private landowners to test out some of the techniques and scaling prior to taking them onto the federal lands. Because again, once we get onto the federal lands, we often do have a more rigorous permitting and compliance environment that requires more data, more proof of concept to be able to move forward with public comment. And as is the case throughout every industry right now, is we are having a lot of workforce issues related not just to the science and monitoring, but to who's doing the work and who's available to implement these sorts of projects, plan these sorts of projects. And so there are a lot of opportunities to sort of tinker with the car while we're driving it, so to speak, to implement large-scale projects that also incorporate the research that we need to understand what happens at scale for these projects. But as is often the case with restoration and a lot of conservation practices, is it requires a level of coordination among the project managers, the folks responsible for the land stewardship, whether managers or owners, and sort of the understanding of the complex and often variable permitting environments that we meet when we get there. That really means we still do just have to be opportunistic about where we go with these things to see what happens, which is, as I was previously in an academic position that was studying some of this and wondering, you know, like, well, gosh, why on earth would you do it this way? And you really do begin to appreciate being out on the ground, how much it's really driven by you have a chance to do it here. We've got a little bit of funding. We got to go while the going's good. And so I think just continued conversation among the researchers to take advantage of the opportunities presented by project sites where there are some potentially interesting landscape scale practices going on, and then increasing some of the coordination both via Farm Bill funding availabilities and statute to start transitioning some of these private lands innovations into public land management to, again, test it repeatedly at scale. I've got a variety of other slides, but we are over time. So I'll thank you all for, again, inviting me and having me here. And yeah, we'll leave it there.
Great. Thank you so much, Carolyn. I know we are over the hour. Thank you so much for those of you who've stuck with us. I did post the emails of our speakers in the chat box. If you would like to reach out to any of them with further questions, you can always reach out via me as well. Just britt.parker@noaa.gov. So thank you so much. And we hope that you can join us for our April webinar, which will be April 25th of this year. And we'll talk to you soon. Thank you very much.